Hey everyone, welcome to the Peter Attia Drive. I'm your host, Peter Attia. The drive is a result of my hunger for optimizing performance, health, longevity, critical thinking, along with a few other obsessions along the way. I've spent the last several years working with some of the most successful, top-performing individuals in the world, and this podcast is my attempt to synthesize what I've learned along the way to help you live a higher quality, more fulfilling life. If you enjoy this podcast, you can find more information on today's episode and other topics at peterattiamd.com. Hey everybody, welcome to this week's episode of The Drive. I'd like to take a couple of minutes to talk about why we don't run ads on this podcast. If you're listening to this, you probably already know, but the two things I care most about professionally are how to live longer and how to live better. I have a complete fascination and obsession with this topic. I practice it professionally, and I've seen firsthand how access to information is basically all people need to make better decisions and improve the quality of their lives. Curating and sharing this knowledge is not easy, and even before starting the podcast, that became clear to me. The sheer volume of material published in this space is overwhelming. I'm fortunate to have a great team that helps me continue learning and sharing this information with you. To take one example, our show notes are in a league of their own. In fact, we now have a full-time person that is dedicated to producing those, and the feedback has mirrored this. So all of this raises a natural question. How will we continue to fund the work necessary to support this? As you probably know, the tried and true way to do this is to sell ads. But after a lot of contemplation, that model just doesn't feel right to me for a few reasons. Now, the first and most important of these is trust. I'm not sure how you could trust me if I'm telling you about something when you know I'm being paid by the company that makes it to tell you about it. Another reason selling ads doesn't feel right to me is because I just know myself. I have a really hard time advocating for something that I'm not absolutely nuts for. So if I don't feel that way about something, I don't know how I can talk about it enthusiastically. So instead of selling ads, I've chosen to do what a handful of others have proved can work over time, and that is to create a subscriber model for my audience. This keeps my relationship with you both simple and honest. If you value what I'm doing, you can become a member. In exchange, you'll get the benefits above and beyond what's available for free. It's that simple. It's my goal to ensure that no matter what level you choose to support us at, you will get back more than you give. So, for example, members will receive full access to the exclusive show notes, including other things that we plan to build upon. These are useful beyond just the podcast, especially given the technical nature of many of our shows. Members also get exclusive access to listen to and participate in the regular Ask Me Anything episodes. That means asking questions directly into the AMA portal and also getting to hear these podcasts when they come out. Lastly, and this is something I'm really excited about, I want my supporters to get the best deals possible on the products that I love. And as I said, we're not taking ad dollars from anyone, but instead what I'd like to do is work with companies who make the products that I already love and would already talk about for free and have them pass savings on to you. Again, the podcast will remain free to all, but my hope is that many of you will find enough value in, one, the podcast itself, and two, the additional content exclusive for members. I want to thank you for taking a moment to listen to this. If you learn from and find value in the content I produce, please consider supporting us directly by signing up for a monthly subscription. My guest this week is Dr. Bill Harris. Bill is an internationally recognized expert on omega-3 fatty acids and how they can benefit patients across a broad range of medical conditions, but in particular with attention to heart disease. He's a professor in the Department of Medicine at the Sanford School of Medicine in the University of South Dakota. He's also the president and CEO of Omega Quant, which is a company he started about 10 years ago that we spent a little bit of time at the very end talking about. And again, the caveat being, of course, he does have a vested interest and therefore a conflict with respect to the involvement of his company. But, I can say I've known Bill for 10 years, and I know people who have known Bill for much longer than that. And his reputation amongst his peers is really someone who is a very honest broker of the science. He's been the recipient of 5 NIH grants for the study of the effect of omega-3 fatty acids, particularly EPA, DHA, on human health. He's published over 300 papers on the topic, and we discuss just a couple of those here, some of the really interesting ones. And he was also the author on 2 of the American Heart Association scientific statements on fatty acids. He earned his Ph.D. in human nutrition from the University of Minnesota and did a postdoc in clinical nutrition and lipid metabolism with Bill O'Connor at Oregon Health Sciences. I was introduced to Bill, like I said, probably 9 years ago from Tom Dayspring. And this was around the time that I was really searching for insight around the polyunsaturated fats, and in particular EPA and DHA. And since that time, Bill has been a very generous mentor to me with respect to just one of those guys. You send him an email with a simple question and he responds with a very thoughtful, 600-word response that contains more insight than anything I could have drummed up. We talk about mostly the landscape of polyunsaturated fats here, but this is a great episode. You don't have to know anything going into this episode when it comes to fats. We're going to explain what saturated fats are, monounsaturated fats, polyunsaturated fats, omega-3s, omega-6s. You're going to come out of this and have a better understanding of this topic than if you went to med school and took a course in this subject matter. I think I'm just going to leave it at that. The show notes will be very helpful for this episode because some of this stuff, it really makes sense to be able to look at a diagram as we go through it. And of course, as usual, for subject matter like this, we're going to go heavily into studies, so you'll want to be able to reference those studies and see that. So without further delay, please enjoy my conversation with Bill Harris. Bill, thank you so much for making the time to talk about a subject matter that I think is incredibly confusing and incredibly important. That intersection of things that are confusing and things that are important tends to be a very important and sometimes overlooked intersection in medicine. So with that, I want to thank you for making the time.
Yeah, my pleasure.
How long have you been the guru of this? I mean, for the listener in the background, I give a little bit of your background, but I was introduced to you in, I think, 2011 from Tom Dayspring, who basically said anytime I had a question that had to do with anything around fatty acids, you were the guy to ask. And over the past 8 years, you've steadfastly answered more questions than I can count. Tell me a little bit about how you got to be the guy that knows so much about this.
Just hanging around a long time. So I got my Ph.D. in nutrition in 1978, and I went to work with Bill Connor in Portland, Oregon for my postdoc. His first assignment for me was to study the question of what does the effect of salmon oil on cholesterol levels? Because we were very familiar with the effects of vegetable oil on cholesterol and animal fat, saturated fat, but we really didn't know what a fish oil would do to cholesterol. So my first really metabolic ward study, I organized, recruited subjects, did the protocol, and we fed people huge amounts of salmon oil, basically all of the fat in the diet. So people were eating salmon steaks twice a day, and this was a 28-day inpatient feeding. Well, outpatient feeding, but metabolic ward. And beyond the salmon steaks, they were drinking about 100 milliliters a day of salmon oil, just drinking it straight. And so it was a huge load, 25 grams of EPA DHA per day. And we found that the omega-3s salmon oil did lower cholesterol relative to the saturated fat diet. And it was about the same lowering as we saw with the vegetable oil diet. But the thing that was unique about salmon oil was that it lowered triglyceride levels. And nobody had known that at that time. So we published our first paper on that in 1980. That's really coincident with the time that the Greenland Eskimo studies were finally becoming well known from Eierberg and Bang, and the omega-3s had been sort of discovered in a sense at that time. And so we started chasing omega-3 effects on lipids and platelet function and all kinds of other things. And so I've just been able to stay with it. I've had 5 grants from the NIH to study omega-3 related questions. And so just again, it's been a field that's continued to be fascinating and ups and downs, but enriching. And as you said, it's confusing right now. It's been confusing for most of its history.
That's kind of an amazing story. And I want to come back to that study because it's possible that the listener right now doesn't understand the context of what 25 grams of EPA would mean, but that's a dose of a type of fat we're going to talk about when we get into the nomenclature that is almost unprecedented. And I already have a dozen questions for you about that exact study and were there any side effects such as bleeding noses and anti-anabolic effects and all these things, but I'll refrain from going down that path to instead make sure we can get everybody on the same playing field. So I'm going to start and give a little bit of a framework, but I'm going to very quickly hand the baton over to you to get into the weeds on this a little bit. So obviously fat is one of the 4 or 5, depending on how you look at it, macronutrients, right? So fats, proteins, carbohydrates, ketones, alcohol. And I think most people know that fats come in different chemical families. So you've already alluded to one of them called a saturated fat. And then everybody's probably heard of a monounsaturated fat. And then there are these things called polyunsaturated fats, which then get further divided into these omega-3s and 6s typically, but there are others. Do you want to say a few words about what separates a saturated fat from a monounsaturated fat, from a polyunsaturated fat, and then how we further subdivide those polyunsaturated into the omega-3s and 6s? And I guess if you can answer the question, Bill, not just through the chemical explanation, though I'd like you to provide that, but also through some of the examples and characteristics of each of them so that folks have a sense of what we're talking about.
From a chemical structure point of view, a saturated fatty acid is a long single chain of carbon atoms all hooked together. And there are what we call single bonds between each carbon atom. In chemistry, you can have single bonds, you can have double bonds, you can have triple bonds. But in a saturated fatty acid or a saturated fat like lard or butter, any of those saturated fats have the vast majority of fatty acids that make up those fats are saturated, meaning they have long single chain. And they're solid at room temperature. I think that's the most common characteristics. The simplest way to detect a saturated fat is at normal room temperature, they're solid. Monounsaturated fatty acids are the next class, and these have the same long carbon chain. It can be 12, 14, 16, 18 carbons long. And there's one double bond in a monounsaturated fatty acid. So when there's a double bond in a molecule, it now has a point of unsaturation. And why they pick that nomenclature is not worth talking about at the moment, but that's what that means. The classic oil that is rich in monounsaturated fatty acids would be olive oil and canola oil now too. Those are both very rich in monounsaturated fatty acids. They are liquid at room temperature, but you put them in the refrigerator and they'll get hard. That's kind of a way of telling a monounsaturated rich oil. If it's out at room temperature, it'll be liquid. In the fridge overnight, it'll get solid or certainly get very cloudy. The polyunsaturated, the next group, it's really instead of one double bond, now we have 2 or more double bonds, and that's the poly. So again, the same long carbon chain with now 2 or 3 typically. Actually, in foods, all you really find is 2 double bonds. The oils that contain polyunsaturated fatty acids are liquid at room temperature, and they're typically liquid in the refrigerator too. You have to put them in a freezer to get them to get solid or to get cloudy. Even some fish oils will not get solid even in a freezer. But the polyunsaturated fatty acids are, again, they are what you find in oils. We say fats and oils. When we say fats, we're usually talking about things that are solid at room temperature. Oils, we're talking about things that are liquid at room temperature. And again, the oils are going to be mono or polyunsaturated rich, and the fats be saturated fat rich. Again, we're now in the polyunsaturated fat world, we have 2 major families. It's called omega-6 and omega-3. And they're called omega because when chemists first started naming chemicals, naming fatty acids when they were discovering the structure of them, there was the beginning and the end of the molecule. And the way they designated what was the beginning of the molecule, they called that was the alpha carbon, the first carbon. And the last carbon in the molecule was always the omega carbon, taking from the Greek alphabet, the alpha and the omega, the beginning and the end. So the omega carbon was at the end. If you have an omega-6 fatty acid, it's actually said omega minus 6, means that if you count back 6 positions from the omega or final carbon, you get the first double bond in the molecule. And that's specific for all the fatty acids that are omega-6 family. They all have that characteristic. First double bond, 6 counting back from the omega or final carbon. And the omega-3 fatty acids all have the first double bond in the third position. And that sounds like it really shouldn't, like, so what? But actually, chemically, it makes quite a bit of difference in the physical properties of the oils, as well as the other molecules or metabolites that these fatty acids are converted into by enzymes in the body. So that's the omega-6, omega-3 family. Fish oils are the ones that contain omega-3, predominantly. Vegetable oils, safflower oil, corn oil, sunflower oil are rich in the omega-6 fatty acids.
It would have taken me an hour to have tried to explain that, Bill, and it would have been half as clear. So thank you for that. The thing that's always amazed me is how many different pieces of information can be conveyed in the nomenclature of fatty acids, because you're dealing with the extent or degree of saturation, anywhere from fully saturated to not, as mono and poly. You then have the actual number of carbons in the molecule, and then you have the position of that first double bond in the case of the monos and the polys. So even for someone who's taken a course in organic chemistry, like, it still requires a little bit of thought when you're looking at detailed chemical drawings of these things. And I suspect that represents at least some fraction of the challenge that people have when talking about this, is we tend to distance ourselves from what we're talking about because of the confusion. But as you point out, it sounds like it shouldn't make that much of a difference, right? The difference between coconut oil and olive oil is one double bond, and yet their properties are almost entirely different. I don't know if you have insight into this, but from a nutrition standpoint, does the specificity of enzymes for these fatty acids, is that kind of unique in terms of just how much difference you can see in the output relative to the starting structure? Or do you see that to be relatively conserved across all of nutrition, outside of fats, that is?
No, I think it's probably a truism that every molecule is unique. Every molecule is special. In our foods, in our bodies, from water, which is probably the most special molecule in the world or in the universe, which makes up, 70% of our bodies, down to the fats and fatty acids. And of course, carbohydrates and proteins are all very unique molecules. I appreciate you mentioning the number. I should mention how they are numbered in case people ever see them written out in the number format, because any saturated fatty acid, let's take a fatty acid that has 16 carbons, and it's a saturated fatty acid. Its common name is called palmitic acid. It comes primarily from palm trees, palm oil. So it's called palmitic acid. Its designation is 16:0. 16 means how many carbons are in the molecule. The colon, what follows the colon, is the number of double bonds in the molecule. So all saturated fats is just a number, colon, and then a 0. When you get into monounsaturated fats, again, it's the carbon number first. Like the most common one is 18 carbon fatty acid, 18:1. And the 1 tells you there's one double bond. That fatty acid is called oleic acid. We get oleo from that word, oleomargarine. Once you start putting a double bond in a molecule, now you have to tell the reader where it is in the molecule. And to your point, when you have an 18:1, you got to know where is that thing. And in this case, it's at position number omega-9. It's the 9th position back from the end. So that'd be 18:1:N. Oh yeah, here we go. Here's the other confusing part of it. We say omega. We like to say omega-3, omega-6, omega-9, but chemists like to talk about them using the term N, like the letter N. It's the final carbon in the molecule, is the nth carbon. It's the last one. It's just the nth one. Exactly where they came from, I don't know. Sometimes you'll see an omega-3 fatty acid called an N-3 fatty acid. N-3 fatty acids, same thing. We're talking about the same molecule.
I think there's mathematicians that have snuck in there so that the nth terminus is where that N must have come from in a geometric series or sequence.
Yes.
We're going to include a lot of figures in the show notes that go through what these pathways look like, because at least for me, I don't find I can wrap my head around these things without actually looking at the chemical structures. And I still remember probably a figure you sent me 8 years ago that really walked through the pathway from linoleic acid and alpha-linoleic acid all the way down through the desaturases, elongases, all of these enzymes. And I think I just had to decide, look, I'm going to sit here and I'm going to learn this. And I remember printing it out, laminating it, carrying it around with me. and just going through it. It's like, okay, well, it's a desaturase. Okay, that makes sense. It's an elongase. It's going to elongate here one, da, 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 da. And at least for me, that was just sort of the way to do it, which was just, I'm not going to be intimidated by all of these names that by themselves don't mean much to me. But if I can look at them in the context of what you just said, which is they're simply referring to positions of double bonds and things, it makes it a little easier. Now, of course, I think most people listening to this are going to be like, okay, guys, why are you going so far into this? And I think the answer is these fatty acids basically make up the most important parts of our body, right? I mean, every membrane of every cell is formulated with these, and it seems that they have a profound impact on our health.
They do. And we're just discovering that more and more.
And there seem to be quite differences. I mean, on the one hand, I'm struck by the relative convergence that you can see across people consuming vastly different things. So there's sort of a dampening effect, if you will, that the body can do, where it kind of converges all sorts of inputs to modestly banded outputs. But at the same time, I'm struck by the differences. So I'll give you one example, which is in the weeds clinically, but it's hopefully for the listener gives them a sense of why we want to understand this. So when we do blood tests on patients, one of the things we always like to do is look at the EPA, DHA, AA levels in their red blood cell membranes. And the laboratory will spit out what percentage is EPA, DHA, total saturates, total monounsaturates, et cetera, et cetera. The ranges on those are not that big, and most people tend to fall within them no matter how much they're eating, but they can be at really different ends of those ranges. So you don't have people that differ by 2 and 3-fold, but people can definitely differ by 20 or 30%. That's my observation. Is that fair?
That's true. That's true. And because when you're talking about a blood test, and specifically you're talking about a red blood cell, which is the test we like to do, and measure the fatty acid composition of the membrane, as you alluded to, every membrane of every cell is made up of fatty acids. And I would venture to say that there is a unique suite of fatty acids, a unique pattern of fatty acid for every type of tissue and every cell. It's not the same anywhere. They're all a little bit different. And that's because the body and the way, the wisdom of synthesizing cells, each cell has its own role to play in metabolism. The membrane has to have certain physical characteristics, being real loose and floppy or being real stiff, depending on the need of that cell. And the fatty acid composition is unique to afford a certain kind of chemical flexibility. It's an amazing thing. There is certainly much wider variation in the fatty acids we eat than when we see in our blood. That's because the body is making the membranes from the raw materials we eat, and it picks what it wants, and it puts the fatty acids largely where it wants them to be. When you're making a red blood cell in the bone marrow, the fatty acids that are selected and put into that membrane are taken out of the blood, and the bone marrow takes what it wants. You can influence it a little bit, but you can't influence it like 2 and 3-fold different for most fatty acids.
To give you one real example that is just a great illustration of this, if you take somebody who is on the lowest fat diet in the world, or specifically someone who, for example, goes out of their way to avoid saturated fat, someone who's consuming in the neighborhood of 10 grams per day or less of saturated fat, and you counter that with someone who's on a super high fat diet that's eating 75 grams a day of saturated fat or more, you might see a 20% difference or a 10% difference in the amount of saturated fat within their cell membranes. As you said, the body tends to be a heck of a lot smarter at putting things together than just doing it based on what's available in the diet.
Yeah, thank God that's true.
Let's talk about why this stuff matters, and let's maybe take a step back and go to back to 1980. So you do this experiment where, and I guess just to set the context for listeners, in 1980 is really, we're witnessing the height, or I would say sort of the wave is about to crest in the major fat phobia 15, 20-year run that's about to sweep over America. In 1977, George McGovern, presiding over the Senate Select Committee on Health, basically comes to the conclusion that even though the evidence against or implicating saturated fat in heart disease, even though that evidence is not great, it's good enough, and they have to make a decision. And the decision that's put forth at that time is that Americans should greatly reduce their intake of saturated fat. I suspect that it's that decision that largely triggers an enormous interest in the type of work that you carried out as that first paper, that first major experiment you led as a freshly minted PhD student, which was, well, gosh, if saturated fat is going to do this, does polyunsaturated fat do the reverse? And at that point in time, Bill, if I'm not mistaken, there had already been a number of studies that had suggested that, broadly speaking, polyunsaturated fats, mostly omega-6s, actually showed a reduction in total cholesterol. Is that correct?
That's correct. In fact, in those days, even starting back in the 70s, people were taking tablespoons of vegetable oil to lower their cholesterol. It was taken as a medicine.
What is the mechanism by which taking tablespoons and tablespoons of sunflower oil or corn oil would lower a person's cholesterol?
It's complicated. It's been fairly well worked out since. But what that does, again, we mentioned what you eat is not directly reflected in your cell membranes, but when you're taking the omega-6s or the omega-9s, the monounsaturates, you're replacing some saturated fatty acids in the membranes. If you're reducing your saturated fat intake, like McGovern et al. Suggested or said we should do, you're reducing the amount of saturated fat to an extent in your membranes, and that has an effect on the physical, chemical fluidity of the membrane. And there is buried within all of our cell membranes hundreds and thousands of these receptors, proteins that are sitting right in the middle of membranes. One of these is called the LDL receptor, low density lipoprotein, which is the primary lipid particle that carries cholesterol in our blood. And that receptor is sitting there in the liver membrane. And if you remove saturated fat or lower the amount of saturated fat in that membrane, changes the properties of the membrane so that that LDL receptor is more efficient at removing and binding to and removing LDL particles from the blood. That essentially lowers your cholesterol level.
So the cholesterol lowering comes through more lowering of the LDL than the HDL?
Correct. It's the LDL that's affected primarily by the saturation of fats. There's some effect on HDL cholesterol, but most of it is LDL.
On the surface, that would sound like a very positive thing. So as tempting as it is to sort of look back at the low-fat mania that swept across America 30 years ago or 40 years ago and just sort of dismiss it as buffoonery for a handful of reasons, especially with the sort of substitution of what became the go-to default, based on just the mechanisms and the studies of the day, it was not an entirely unreasonable thing to suggest.
No, but particularly, as you said, McGovern committee said saturated fat should be reduced. Didn't say all fat. And I think that's where the message got mixed. Because if Americans had just reduced saturated fat and replaced it with mono and polyunsaturated fats, we wouldn't have had this problem.
It seemed to get replaced by sugar was one of the big things that got.
Right. It was take all the fat out. And that was the mistake.
The question you were trying to ask when you did that study where patients were consuming, in the end, I think you said 25 grams of EPA. And I guess I should, before you answer this, maybe let's go back and explain what EPA, DHA, and all these other things are. And again, assume for a moment, Bill, that there will be a large figure. Multiple figures, in fact, will be in the show notes. We'll have the really detailed chemical ones, but we'll also sort of have the cartoony ones. So let's assume that someone's looking at the cartoony figure that takes linoleic acid down to arachidonic acid, and then the one that takes alpha linoleic acid down to EPA and then down to DHA. Can you explain what's happening there? And let's start with the omega-6 one, I suppose.
Sure. The left-hand side of the slide that I have in my mind, and I think you have in your mind.
I'm probably having in my mind a slide you've shared with me, but we will make sure we use exactly whatever you're speaking from in memory now.
It's always done this way for some reason. The left hand is always the omega-6. So it starts with linoleic acid, which is an omega-6 fatty acid. It's the principal omega-6 fatty acid in our diet. It is an essential fatty acid with a capital E, essential, meaning we cannot make it. It's very much like a vitamin. Can't be made from scratch, and it is important for metabolism. So it is an essential fatty acid. Hey, we have to eat some omega-6.
And what are the dominant sources of that, Bill?
Vegetable oils. Soybean oil is probably, 80% of where we get our linoleic acid in our diets.
So sunflower, corn, soybean, cottonseed would be the big four, right? As my recollection.
Yeah, actually, sunflower and safflower nowadays are not. Linoleic has been pretty much stripped out of those oils. Now they're what's called high oleic safflower. It doesn't say it on the label, but what's in the bottle has vastly changed from the natural fatty acid pattern. But corn and soybean are still high omega-6, meaning 50-60% of the fatty acids in that oil are linoleic acid. And linoleic is an 18 carbons, so it's 18:2, two double bonds, omega-6 position. So what happens is you eat that, and a portion of it is glommed onto by certain enzymes in the liver that want to make a longer fatty acid. And so they add 2 carbons, and they get a 20-carbon fatty acid now. And then the liver has enzymes that will add, instead of having 2 double bonds, it'll now have 4 double bonds. It goes through a 3 double bond molecule, and now we're at a 4 double bond. When you get to this molecule, it's an omega-6 family, 20 carbons, 4 double bonds. That's called arachidonic acid. And that is an extremely important fatty acid in metabolism. If your listeners have ever heard of prostaglandins, this is the stuff of which most prostaglandins are made. It's the substrate. It's the beginning, and it's terribly important throughout the body. The liver can even take that molecule and make it even longer, 22 carbons, and add more double bonds, up to 5 double bonds. But there's not much of that around, and we really don't know what it does. I think the most important endpoint of omega-6 metabolism is to produce arachidonic acid, 20 carbon, 4 double bond.
Well, the way you explain it, like I think going back to the biochem, anyone who's listening to this who's a college student or a med student or something, I mean, that's not rocket science, right? You elongate it with the elongase enzyme, and then you further desaturate it, take 2 of the saturations out, and there you go. So you go from 18.2 to 24. Now, arachidonic acid has a real bad rap, doesn't it?
It has, yes.
We'll get into it in detail, but just, is it safe to say that that's a bit misunderstood and that the binary view of arachidonic acid might not be the whole story?
That's safe to say.
All right.
I would agree with that. We'll get into that later then.
So we'll come back to the demonization of arachidonic acid. Let's go over to the right-hand side of the picture we both have in our mind that is hopefully about the same picture.
It is, right? Now we have at the top, instead of linoleic acid, we have linolenic acid. Just add one N to the name, and you get linseed oil. Most people are familiar with linseed oil. That is rich in this particular fatty acid. Flaxseed oil is similar. Chia seed oil, but are all sources of this linolenic acid. It's 18 carbons, again, same length as the omega-6 cousin. It has 3 double bonds instead of 2, and the first double bond's in the omega-3 position. So it's an 18:3 N-3 fatty acid. It also is essential in the same sense that the omega-6 cousin linoleic is essential in the diet. This is called alpha-linolenic acid, is also essential. We can't make it, and it's important for metabolism and health. And so the same game happens. This 18 to alpha-linolenic acids, we call it ALA, thank God. ALA is consumed and then again goes to the liver and is elongated. In other words, 2 more carbons are added and more double bonds are added to the molecule. So it goes from 3 to 4 to 5 double bonds. And now you have 20 carbon, 5 double bond, omega-3 fatty acid, and that's called EPA. The EPA stands for Eicosa, E-I-C-O-S-A, which is 20 in Greek. Penta is 5, because there's 20 carbons, 5 double bonds, and then we say enoic acid means it's a fatty acid. So it's a 20 carbon, 5 double bond molecule. And that's EPA, one of the 2 most important of the, quote, omega-3 fatty acids. That fatty acid then, EPA, can then be further converted to 2 more carbons, again, elongates the chain and desaturates, replace single bonds with double bonds. So you end up with a 22 carbon, 6 double bond molecule. And that's called DHA, which stands for docosahexaenolactone 22 hexa 6 enoic acid. So it's a 22 carbon 6 double bond. So EPA and DHA are the two. When people talk about omega-3s, that's what they mean. Those two fatty acids are the principal ones.
Going forward, just to make everybody's life easy, we're going to talk about ALA, alpha-linolenic acid, as the omega-3 that you get mostly out of flaxseed and chia seed, I think. Are there any other sources of high dose of ALA?
Well, no, not a high dose, but if you look at what's the principal source in the American diet, it's soybean oil.
Soybean and maybe canola to some extent has a little bit?
To some extent, yeah. But soybean is it's the gorilla in the room when it comes to vegetable oils in America. And it's about 7% of the fatty acids in soybean oil are ALA.
ALA goes through a number of steps, adds a couple carbons, desaturates a couple bonds, and you have EPA. Though I don't think you stated this, I do believe there's an equilibrium. EPA and DHA can go back and forth between each other, or is that mostly a one-way street?
We thought they kind of went back and forth, but now I think we know, based on a paper that was published a couple months ago, it looks like EPA goes to DHA. DHA does not, what they used to call it is, gets retro-converted. In other words, goes from a 22 carbon 6 molecule to a 20 carbon 5 double bond molecule. That's retro conversion, going backwards. We thought it happened. We don't think it happens anymore.
It's more straightforward than what I used to.
Yes.
My laminated sheet's got to be updated. So it's basically ALA to EPA to DHA on the right-hand side of the page. That's your omega-3 family. And then for the sake of simplicity, we're basically going from LA, linoleic, not linolenic, linoleic acid, down to arachidonic acid, AA. So LA to AA is your big omega-6 pathway. We'll pause there for a moment. With all of that said, what was your state of understanding circa 1978-ish, whenever you probably started this study, about EPA and DHA, which today we know a lot about and we'll talk about it, but what did you know then?
I didn't know anything about them. All I knew was we were using salmon oil, and I don't remember, at the beginning of our experiments to see what the effect of salmon oil was on cholesterol, I'm not sure I even knew EPA and DHA existed. In a very simple-minded way, we were asking the question, we know animal fats that are solid at room temperature raise cholesterol levels, and we know that vegetable oils, plant fats, basically, plant oils, lower cholesterol, and they're liquid at room temperature. So we have animal and solid, and we have vegetable, plant, and liquid. So is it the liquidness that's important, or is it the animalness, animal versus plantness, that's important in controlling cholesterol levels? And so the uniqueness of fish oil is it comes from an animal, but it's a liquid.
That's really a funny and cute way, yet an elegant way to think about it, right? It's a 2x2 of solid versus liquid, animal versus plant derived, and the fish oils sit in a unique part of that 2x2, as you said, liquid but animal derived. Okay, so that makes sense.
That was the question. So is it the animalness or the liquidness of the oil that lowered cholesterol? It turns out that fish oil lowered cholesterol, and it's an animal fat. So it's the liquidness that was important, not the source, not whether it's a plant or an animal. It's the physical property of the oil. That's the important thing. But EPA and DHA, I don't remember knowing anything about them until well into our study, and I started reading the papers from the Greenland Eskimo studies. And that's when I said, oh, these things have EPA and DHA in them. How about that?
Now, the average American today who is not supplementing with fish oil will get approximately how many grams of EPA and DHA in their diet?
Well, let's talk about milligrams, because it's about roughly 100 to 150 milligrams, 0.15 grams per day is about the average, EPA plus DHA.
You mean 150 milligrams combined EPA and DHA?
Yeah, right. It's about how much arachidonic we eat, too, as a matter of fact. It's about the same scale.
That's kind of mind-boggling when you think about how much fat the average person eats, right?
Oh, yeah. Yeah. Out of 80 to 100 grams a day, that 0.15 grams might be EPA and DHA. That's too bad.
Historically, was there a day when we consumed more of that, or where is that in line with history?
Certainly any culture that lived off seafood was eating more EPA and DHA.
So let's use the Okinawa as an example. Up until not including this generation, which I've read have sort of fallen off the rails. But if you go back a generation and beyond of the Okinawa, who obviously would have been consuming seafood daily, how much EPA and DHA would they have consumed?
They were probably in the neighborhood of 1.5, maybe 2 grams a day, 2,000 milligrams maybe. I mean, the Eskimos, when they were discovered by Dyerberg and Bang in the 1970s, documented 6 to 7 grams a day of EPA and DHA.
As impressive as that is, let's come back to your study. You were giving 25 grams of EPA and DHA to these subjects. So there had probably been I assume that your rationale for doing this was, if this doesn't show an effect, we never need to study this again.
That's exactly the rationale. Do it once.
What was the magnitude of the reduction in total cholesterol, LDL cholesterol, and triglyceride that you saw in that study? Not to put you on the spot with something you did 100 years ago, but directionally, was it significant? Not just statistically, but clinically.
Oh, no, it wasn't marked. Like cholesterol might have gone from 250 to 230.
Okay. What about triglycerides?
Triglycerides went from about 100 to 75.
Okay, so that's a pretty big reduction in triglycerides. It's
as a percent, it is.
Yeah. Any other phenotypic changes you observed in those subjects, or those were your primary endpoints? That's all you had the budget to study?
You alluded to it earlier. Platelet function, bleeding was something we looked at because by that time, Jorn Dyerberg had published a paper in Lancet in 1978 proposing that EPA was an antiplatelet, or like a blood thinning fatty acid, and that is why it prevented blood clots, and that is why Eskimos didn't have heart attacks. That was the proposal. And EPA had been shown by that time to be antiplatelet. So we were very interested in the effect on bleeding. And we saw a significant prolongation of an old-fashioned test called the bleeding time test, where we actually cut the skin and count how many seconds it takes to stop bleeding. It didn't prolong it any longer than aspirin did, so not outrageous, except in one patient. It wasn't a patient, it was a college student. But he had a marked drop in his platelet count. We wrote a whole paper on this guy. He had a marked drop in his platelet count, a really prolonged bleeding time, and we stopped him on the omega-3 diet because of that. But everybody else had just kind of a mild prolongation of bleeding, which was so the platelets were less reactive, less likely to clot, which is a good thing. So that fit with the idea that these are protective against heart attacks.
Now, if I did the math somewhat correctly on your salmon burger versus salmon oil distinction, is it safe to say they were getting about 2/3 of their EPA and DHA through consumption of salmon and about 1/3 of it then through actual concentrate oil?
It'd probably be the reverse, because let's say they were getting 2 4-ounce servings a day of salmon, and let's just ballpark that at 2 grams. Let's be generous. Say that each one of those has 2 grams of EPA and DHA. So there's 4 grams, and then they were getting 20 grams from the liquid oil they drank. It was almost,
I don't know why I thought it was only 10. Okay, so that was the reverse. So they're getting most of it in concentrate. They're getting, maybe 1/4 of it or even less potentially through consumption of salmon. Going back to the Eskimo for a second, do you have a sense from those studies what percentage of their total calories were fat, and then how much of that was saturated versus poly? And I'm guessing mono was not a very abundant source in the North Pole.
Very high fat diets. Again, I'd have to look it up, but their diet was largely seafood. And we're talking about seal, blubber, and whale meat, and some fish. This is pretty much what they ate. Greenland, you don't grow anything, at least not until global warming comes along. But for now, they didn't grow anything. So fruits and vegetables and grains you could get them at an occasional store, but fundamentally they were living a traditional lifestyle in eating what they killed out of the sea. So they were probably 80% of their calories were fat.
And of that, do you have a sense of how much was polyunsaturated versus saturated?
Probably about maybe 6 or 7 grams a day out of, let's say they ate 100 grams of fat a day. So 6 or 7% of it might have been the omega-3, the polyunsaturates, very little omega-6. And probably 70% of the fat was saturated. Huge amount. I mean, this is what was so amazing about the Eskimo studies, because we had this paradigm that high fat, high saturated fat, high cholesterol, of course, they're eating very high cholesterol diet because everything was from animals. Those are bad diets. And yet the evidence, which has been challenged nowadays, but at the time, the evidence was these Eskimos were virtually free of acute myocardial infarction, of heart attacks. It just didn't make any sense, which is why the couple of Danish investigators went over there and started studying them, measured their plasma, their food, and they kind of discovered omega-3 fatty acids.
So was your conclusion from the study in 1980 that the high amounts of EPA and DHA in their diet were offsetting or protective to the high amounts of saturated fat? Or was your conclusion that maybe the saturated fat, because it came from fish, was somehow different from, say, dairy or land animals? I mean, how did you reconcile your experiment with this broader volume of data, though, they're obviously asking very different questions and looking at very different things? I mean, how did you begin to square those things?
For one thing, again, we didn't feed any blubber or any whale meat or seal meat, any of that really high. So we were feeding salmon oil.
Your subjects didn't really have a significant increase or change in macros, really. They were just basically getting an extra 25 grams of fat that happened to be polyunsaturated omega-3, but they weren't.
That largely true.
So where do you go next, Bill? So obviously, well, you've never stopped looking at polyunsaturated fats since. So tell me how that study basically piqued your curiosity.
I think the interesting thing, the way that played out, is actually 1985 was a turning point year for omega-3. In that year, in May of that year, the New England Journal published 3 back-to-back omega-3 studies. One was our study in giving very high doses of omega-3 and looking at effects on lipids. And we showed huge drops in triglycerides because we were studying people. Some of the study I did was with the normal volunteers. We later did studies with people who had lipid disorders, had very high triglyceride levels, for example. And we found that giving them fish oil just knocked the socks out of their triglycerides. Instead of their triglycerides being 2,000, they were down to 250. It was a huge effect.
And how much EPA and DHA did you have to give them?
That was the 18 to 20 gram. We were still playing the same game. We were still giving high doses of salmon oil. So New England Journal publishes our paper. It publishes a paper on kind of arthritis or inflammatory disease, and it publishes a paper on kind of molecular biology, the effects of EPA on what's called leukotrienes in inflammatory molecules. It was a basic science paper. But it was bang, 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 3 papers in a row, literally in the magazine in a row, in May of 1985 that just put omega-3s in lights on the map. And people got very excited about them. What we did subsequent to that, instead of patients completely controlling their diet, by that time we were able to, because omega-3 supplements, concentrated pills were now becoming available. And so we did some studies just giving 18 capsules. So we were giving 6 grams a day of EPA and DHA in capsule form without changing anybody's diet. What happened in that setting was very different. In that setting, where we didn't change their background fat intake, just added omega-3s, triglycerides still came down very nicely, but the conundrum was LDL cholesterol, the bad cholesterol, started to go up. That was one of the downsides of the omega-3 story, because all of a sudden we publish this, it gets a lot of press, American Heart Association, and these fish oil companies that were just starting to advertise their product as cholesterol lowering, based on our earlier studies and others, it's not just us. Fish oil folks were marketing their fish oils as cholesterol lowering products. And then we show, when we directly test them, that they don't lower cholesterol. In fact, in some people at high dose, they will raise cholesterol. So FDA sends out all these letters to these companies and says, you can't, you're false advertising. You can't say this anymore. So that was what they call a gut punch to the industry at that point.
At the time, was it clear whether LDL cholesterol alone was going up, was ApoB going up as well? What other parameters of the lipoproteins were changing?
LDL cholesterol and ApoB. So there were more particles.
How much were they going up based on just this 6 grams of additional EPA and DHA?
They might have gone from an LDL of 120 to 140 or 150.
That's amazing. I mean, we're talking about 6 additional grams of a very specific type of fat having that much of an impact on LDL cholesterol and presumably, as you said, the particle number or ApoB. So mechanistically, what do you think was happening there?
That's been hard to figure out, but more recent studies have suggested that there's actually an effect primarily of the DHA component on LDL receptor activity. It actually can slow down the action of LDL receptors, so the LDL receptors are not removing LDL particles from the blood as fast as they used to be, so the blood levels go up. So it's an effect on clearance, it's not an effect on production.
In the previous example, were you saying that the part of the saturated fat issue on clearance, because there's obviously a big effect of saturated fat on production, but you're saying that saturated fat on clearance was altering membrane permeability and the LDL receptor was therefore losing efficacy?
Yeah, right. That's, I think, our current understanding of why saturated fats raise cholesterol, raise LDL. Now here, several years later, we kind of begin to see evidence that fish oil, and again, I want to emphasize this is in people that have high triglyceride levels. This is not just in normal people taking one fish oil pill. This is completely out of that realm. We're 6 grams a day of EPA and DHA in people with elevated triglycerides. In that setting, the LDL and ApoB went up.
Now, there's another little wrinkle here, Bill, which is if you're going to take people that have triglycerides that are that high, how many of them are insulin resistant or have metabolic syndrome as the underlying disease state versus how many of them are metabolically very healthy but have a hypertriglyceridemia, a familial, I think that's a Friedrichsen-Lewy-Lees type 3, but I'm probably wrong on that. But how many of them are genetically seeing this high triglyceride in the context of perfect metabolic health versus metabolically ill?
Yeah, that's a good question. And I'd have to look back. I mean, you're right about Friedrichsen types. It's not type 3, it's type 4, which is the isolated hypertriglyceridemic person. And there's type 2B, which is high triglycerides and LDL. In both of those settings, the LDL cholesterol went up. We had never heard of metabolic syndrome in the mid-'80s. We'd have to look back, what was their glucose level? I'm not even sure we measured it. I'm sure we measured their blood pressure and their body weight, but other metrics of the metabolic syndrome weren't even crossing our minds in those days. So it's hard to say.
That's interesting. But today, the largest dose of EPA that is given pharmacologically is about 4 grams. Is that correct?
4 grams.
Isn't that indicated primarily for people with elevated triglycerides?
It's indicated for people with very high triglycerides. So we got 2 levels of high triglycerides. You got garden variety high triglycerides, which is maybe 200. So a normal triglyceride may be 100, 150. I mean, maybe that's not optimal, but that's kind of normal. 200 to 500 is what we call hypertriglyceridemia. And over 500 is now very high triglycerides. And there's kind of a bright white line. The FDA indicated when the first omega-3 drug was approved, it was Lovesa or Omicor. And it was approved by the FDA for treating triglycerides over 500, not under 500, over 500. And it was approved at this dose of 4 grams a day because that's the dose that the company did the studies at. They could get better triglyceride lowering with higher doses, but now you're talking 6 or 8 pills a day and it becomes totally impractical. So it was a compromise. Let's make the dose 4 grams a day. It does lower triglycerides and it works to some extent. And so that's what the FDA approved. And so FDA has now set 4 grams as the standard dose.
Their product, is it any different from what one buys over the counter?
That product that I was just talking about, what's called Lovesa, and it's now Lovesa, that's about 85% EPA plus DHA. It's ethyl esters. You can buy over the counter or dietary supplement, essentially, more accurately, dietary supplements that have that much EPA and DHA as ethyl esters in one pill. Typically, you have to buy The pill is not a 1 gram pill. So maybe we're going to get into this, the confusion about 1,000 milligrams of fish oil. But the standard drug, the Lovesa drug, is 1,000 milligram capsule, of which 850 or 85% is EPA and DHA.
Oh, yeah, no, we should definitely cover that now. So if you go on Amazon, I mean, I'll just share my bias. I've talked about it before. The two brands I typically recommend to patients are Carlson's and Nordic Naturals. And I'm sure there are several brands out there that are quite reputable. Anahad O'Connor at the New York Times wrote a story on this probably 4 or 5 years ago, looking at lots of different brands of fish oil. And it was looking to basically see how many of these were made at GMP standard, how many of them actually had in them what they said they contained from a content perspective, what was the level of contaminant, all sorts of variables. But for whatever reason, again, those two brands I've just gotten to know and I've gotten to trust. But you still have to read the label very carefully because, one, these are very large capsules. Two, the entirety of the capsule is not EPA and DHA. So we tend to think about how much EPA and DHA we want, and we then have to sort of reverse engineer it out of the capsules. If you're taking 2,000 milligrams of fish oil, and let's say 1,600 of that is true EPA and DHA, which is 80%, that's not an uncommon finding. What's the other 400 milligrams?
It would be a mixture of some monounsaturates and some polyunsaturates, just a kind of general standard fatty acids you'd find in most foods, just a very small fraction of what's in a fish oil, particularly a fish oil concentrate.
Now, am I being paranoid about this stuff, or do you think that most of these things that are sold as dietary supplements are reasonably safe, or what is your view on that?
I don't have a problem with dietary supplements. I think that the vast majority of them, when they've done consumer reports testing, they've done it twice in my memory, their final conclusion is generally the products have pretty much as much EPA and DHA as they say, and with some variation, and they're free of toxins and any meaningful levels of environmental pollutants. So I don't have a problem with it. If the challenge is if you're going to try and get 4 grams a day of EPA DHA, or 3.5 grams is really what 4 capsules of Lovesa would give you, because it's again 85%. So you're going to be taking a whole lot of dietary supplement, a lot of pills, because most pills are not that concentrated. Typically, nowadays you can find very highly concentrated products, and the line between a drug and a dietary supplement is getting a little bit fuzzy, which is something some of the drug manufacturers are pointing out more and more loudly, that there's a lot of products that are being sold as dietary supplements that fundamentally have the same chemical composition as FDA-approved drugs. There's going to be a fight about this coming on. But the processing of omega-3 rich oils has advanced tremendously over the last 20, 30 years, and they can really concentrate these. Take a raw fish oil, which might have 30% of its fatty acids, EPA and DHA, and you do lots of processing to get rid of all the other fatty acids, and all you have left is EPA, DHA, and you're really highly concentrated. And that's not all that different than the composition of some of these drugs. It's going to be confusing, I think, to the consumer.
Bill, what is our current understanding of the health benefits of EPA specifically? I want to actually talk about this and then do the same thing on DHA and then do the same thing on arachidonic acid. So cover these 3 end products of the omega-3 and omega-6 pathways. But let's come back to omega-3 to EPA, because that's sort of where we got off on this little side tangent. Today, is the consensus view that EPA is a quote-unquote heart-healthy oil? Yes, and you could say the same for DHA, in my view. But yeah, EPA is heart-healthy. Its mechanisms by which it is heart-healthy are multiple, and they include being converted into, again, some metabolites, some prostaglandin-type molecules that make the blood platelets, less likely to get sticky. And so there's it's kind of like taking aspirin without some of the side effects of aspirin. So that's one of the arms of the benefit. The EPA is also able to produce a whole series of molecules that we call resolvins, because they resolve inflammation. So they're kind of anti-inflammatory in that sense. They also, when EPA becomes incorporated into cell membranes, it changes the
flexibility, the fluidity of the membrane, just because of its own physical properties. And that changes the way the enzymes that live in the membranes work in such ways that makes cellular metabolism run more smoothly. I mean, to try to simplify this. Those are really primary ways that EPA, I think, is heart healthy. We've only had one big study with EPA only, free of DHA.
Let's talk about that one now, and then I want to come into potential risks of EPA, and then I want to circle back to DHA. But let's talk about the EPA-only study. What was the patient population, what was the dose, and what was the objective of the study?
The study was called Reduce It, which was an acronym, as they all are, for something. Reduce It was the name of the study. The product was called VASCEPA, like vascular EPA, VASC EPA. The company that makes the drug is called Amarin. And the way the study was done, they gave 4 grams a day of this EPA. It's EPA ethyl ester. So it's a very purified EPA that has a ethyl ester, which is the typical way that they concentrate omega-3s nowadays. 4 grams a day versus the 4 grams of a mineral oil placebo, which has had some controversy as to whether that's a real placebo or not. Roughly 8,000 patients who all were on statin drugs to control their cholesterol levels. And they all still had triglycerides between 2 and 500, roughly 150 to 500. So triglycerides were still elevated even though they were on a statin. Cholesterol, LDL cholesterol was roughly in the 70s. So there was low or healthy levels of LDL. And they also had to have either a history of heart disease or some other risk factors, like having diabetes, for example, was another way you could get in. So if you met that criteria, that kind of patient, you were given either 4 grams of placebo or 4 grams of VASCEPA.
Do we know what fraction of those patients were metabolically ill? I assume most of them were. And I know this study is only about 1.5 years old, right? I mean, I remember this when this came out.
Well, it was reported in November, so 6 months ago.
Oh, wow.
8 months ago.
Yeah. So almost a year. But okay, that's time. I've lost track of time.
Time flies, right? Exactly.
But how many of these people were sort of metabolically super healthy, but just happened to have these genetic triglyceride elevations?
Nobody checked in the study what any kind of, they may be someday. They probably have blood for them and they'll check things later. But as a recruitment strategy, they just took people who met those criteria. You're on a statin, you have triglycerides between 150 and 500, and you've got some other risk factors for heart disease. And that's it. And you're in.
What did the study show? Because it sure made a lot of headlines.
It should have, and it did. It showed a 25% reduction in risk for overall cardiovascular events over about a 4 or 5 year period, which is not that long. And it was effective across, myocardial infarction, need for angioplasty, a variety of different cardiovascular unfortunate outcomes. So it was a big hit. It was really, for the last 15 years, we've been searching for other lipid lowering drugs or other drugs that will improve the outcomes over statins. Because statins have been established in the 80s and 90s and 2000s as very, very effective in reducing risk for heart disease. But there's still people, even on a statin, that still have events, cardiac events. So that's called residual risk. They have leftover risk. So what do we do for that? And there's probably been 10 or 15 drugs that have been tested to try to improve upon a statin. Really, none of them have worked, without going into all the details. But this one, pure EPA, worked, and it worked great. And it worked with virtually no side effects. And you can take it with any other medications. It doesn't have any drug-drug interactions. I think it was a big hit and well-deserved. I should mention the name, the trade name of the drug is VASCEPA. The generic name is called icosapent ethyl. 2 words, and it starts with an I, ICOSA, icosapent. It's really just a flipping around of the spelling of icosapentaenoic acid, or EPA.
Now, Bill, one of the issues with this study, of course, is the inclusion criteria assumes that the patients have very high triglycerides. I must have received 12 emails in the span of a day from patients of mine saying, hey, should I be taking this? To which my answer was, well, your triglycerides are 86, so I'm going to go with no on that because I can't infer that the mechanism by which this worked in these patients is going to have a benefit in you. Do you know if there's any plans to repeat that study or a study like it in a normal triglyceride population?
I don't. I know that what's fundamentally being reproduced is the same type of patient, but with a EPA plus DHA product.
Why was that study done with only an EPA versus a combined?
Well, in the late 80s, a EPA-only drug was approved in Japan called Epadil, which is essentially it's exactly the same thing as Vascepa. In the Japanese, back in the 1980s, believed that it was EPA that was the active agent in fish oils. So a drug company called Mochida developed an EPA drug, and they got it approved, and they've been using that EPA drug for years and years. And the JELIS trial, which was published in 2007, which was a Japanese Omega-3 trial, used this product. It's called Epadil. We would call it Vascepa. And it was successful. This company in Ireland, which Amarin, has the same molecule, essentially. I think they're trying to carve out a unique niche in the omega-3 world that they can get an approved drug. EPA plus DHA is already approved. That's Loveza, Omicor. They said, well, let's just try the EPA part, see what that does. And it works well. What nobody's ever done and nobody is doing yet is the counterpart,
only.
A DHA only study.
What is your take on this from two standpoints? The first is, if you can speculate for a moment, do you believe that EPA and DHA from a cardiovascular standpoint are as beneficial or have benefit in people with normal triglycerides?
Yes. I don't think the cardiovascular benefit comes from lowering triglycerides. In fact, in this study, the Reduce It study I just talked about with EPA, triglycerides were lowered 15%, maybe. It was not a huge drop in triglycerides by any means.
What was the reduction in LDL-C and ApoB? I don't recall.
Yeah, virtually no change.
So unlike PCSK9 inhibitors, which really have had the biggest impact on residual risk in cardiovascular disease over the past 5 years, very similar population to what you've described in Fourier, more so than Odyssey, where they started with patients already maximally statinized. These patients, it was independent of their triglyceride level, but they had to be sort of maximally statinized. I think they came in with an average LDL cholesterol of 74 milligrams per deciliter. And in a very short period of time, something to the neighborhood of 2.5 years, saw an amazing event risk reduction.
But the event risk reduction in Reduce It was greater than the PCSK9 studies.
Yeah, it was a longer study. Wasn't it about 5 years in Reduce It?
Yeah, right.
Yeah, and
right.
Fourier was like 2.2 and Odyssey was about 2.4, which again, I think all of those are amazing. I'm not saying that to be one up on Reduce It or one down. I think most people don't understand the time course of cardiovascular disease well enough to appreciate the fact that you can take a disease that is a time course disease that starts at birth and in somewhere between 2 years and 5 years actually reduce events. It shouldn't happen. And in fact, I remember, I don't know if I actually said it out loud. It would be great if I did, because I could go back and, maybe someone would remember. But I certainly remember thinking Fourier is going to fail, because not that I didn't have faith in the mechanism of PCSK9 inhibition, but because I simply didn't think you could bend the arc of a disease like cardiovascular disease in 2 years on a group of patients who had an LDL cholesterol in the 70s. That just struck me as impossible. It is really quite amazing that all of these things work. And in some ways, it's even more amazing, frankly, that just pure EPA could have this effect. Which, again, I'm bringing you back to the question that I keep interrupting you when you start to answer. I apologize. Why in the world would 4 grams of EPA reduce events, especially, as you said, when it's not the obvious mechanism of, hey, we're going to drop triglycerides, which all things equal should drop ApoB. And by the way, you're seeing a greater magnitude of event reduction than you're seeing with aspirin. So the pure antiplatelet effect also seems a bit counterintuitive. What else do you think is going on here?
Right. It's not enough. Whatever role inflammation, and it's such a slippery word that's thrown around so much. But EPA definitely gives rise to molecules that are pro resolution of inflammation. So inflammation starts, the EPA will shut it down. To whatever extent a cardiovascular event is precipitated by an inflammatory event, the omega-3 EPA could participate in that. It could stop it. The EPA could also play a role in even like the control of the heart rate. The heart rate variability can be reduced. I'm not sure in this study they measured it, but we've done studies with omega-3 showing heart rate variability, which is a marker of autonomic nervous system control of the heart, is improved. So that's another piece of the puzzle. It could just be several different things that each one in and of itself. They add up and they multiply.
And you said heart rate variability improved. Before that, you said reduced, but I think you mean improved or increased, right? Is that what?
Correct.
Yeah.
Correct.
Do you recall if in Reduce It, they measured other cytokines, inflammatory cytokines beyond the usual suspects? Like, did they look at all of the suite of interleukins and things like that? Was that published in the original study? So presumably, as you said, they've got a biobank that may be able to look at other markers of what was the signature of this event reduction? Going down this path you just described, it'd be great to see what happened to IL-1, IL-6, TNF. If you look at all of these other things that could be playing a role in the inflammatory component of atherosclerosis, that would be interesting to see, right? Because then it would give you more confidence that this has broader applicability than just people with sky-high triglycerides.
Back again to the inclusion criteria, these are not sky-high triglycerides. And this is not triglycerides over 500. These are not people at risk for pancreatitis. This is much more garden variety hypertriglyceridemia.
I don't know. In my practice, Bill, 150 to 500 is sky high.
Okay, well, I guess I'm used to hearing, type, 500,000, 2,000. People have that, but that's the place the omega-3s first got their approval in that very high triglyceride world. And so when we bump it down to under 500, to me, it seems like kind of garden variety, but you're right.
Well, but that's a fair point. I mean, it's certainly representative of the U.S. population. Did it look at how much of that EPA converted to DHA? In other words, one of the advantages, presumably, of giving mega dose of EPA versus mega dose of DHA is you're higher up the food chain. So presumably you're covering any benefit that's unique to EPA, if you believe there may be one, and then you're also transmitting into DHA and getting that, or do you believe that all of the benefits of EPA are transmitted through DHA?
I think it's probably all the benefits of EPA are transmitted through EPA, not through conversion to DHA.
Not through the conversion to DHA.
No. In fact, when you look at a couple of papers looked at the effects of giving pure EPA, 4 grams, on red blood cell DHA levels, for example. And DHA levels actually go down a little bit. EPA goes up. Of course, you're feeding EPA. But the DHA component in the red cell membrane goes down. Or in other studies stays the same, but doesn't go up. You're not increasing DHA tissue levels.
That's really interesting. So in other words, if EPA is being converted to DHA, which I assume we still think it is, it's not necessarily, it's just increasing the substrate pool of DHA, but not necessarily the incorporation into cell membranes.
Right.
That's interesting. And that actually explains, I think, some of what I guess I would see when I look at people's laboratory values. While we're on this topic, if I consumed staggering amounts of flaxseed oil, by the way, a friend of mine once gave me a recipe to make flaxseed tea. And it tasted really good when I had it at her place. So part of it is just, it was really amazing. And part of it is the recipe was so complicated that I took pride in taking 2 days to make a vat of flaxseed tea that could feed a small village. I was never able to get it quite right, but let's assume I could get it right and I could consume a near infinite amount of flaxseed oil. Could that amount of ALA ever give me sufficient enough substrate EPA and DHA to rival what we're talking about in these supplemental doses of 4 grams?
No, it's never. When people have tried giving 12 grams of ALA, not just flaxseed oil, ALA.
Just straight ALA.
Yeah, you don't even get. You might take an EPA level of 1% in a red cell and maybe drive it to 2%.
There's two questions I have, and I hope I'm going to remember the second one. Is there a risk that looking at the red blood cell, which of course is the most obvious and easy cell for us to access the membrane in, is there a risk we're missing something that's not occurring in cells that we can't access, like as easily? We can't look at the membrane of adipose cells or muscle cells, and we typically, even though it would be just as easy to look at leukocytes, I assume we don't look at them, at least clinically or commercially. Do we run the risk of just looking at one pony here?
Right. Everything's a compromise. So the red cell is the easiest cell type to get at. Leukocytes are not that easy to get at.
Right. You need some apheresis or something like that.
Clinical lab. Right. In just a clinical lab setting is very difficult. Red cells are thrown away by the gallon day by day, just because all you really wanted was the plasma, right? So the red cells go to the bottom and you take the plasma off and you throw them away. We've shown red cells correlate with quite a few other tissues in terms of the omega-3 levels. So they are a good reflection of other tissues. Probably the only one that's the least reflective of is the brain, at least in the adult. It's hard fatty acid composition of the brain.
Yeah, I don't think anyone's going to sign up for the brain biopsy. So what are some of the tissues that you've seen high correlation with RBC?
Well, we did it originally with the heart, using heart transplant patients who were being followed up every 6 months with a heart biopsy to see how their heart was doing, of course. And we were able to get their red cells and the heart biopsy and measure the omega-3 content and show the nice correlation. The higher the omega-3 in the red cell, the higher the omega-3 in the heart. Other people have done this too. And you can do it in animals, of course. You can look at lots of different tissues.
Is there a high correlation with liver as well as myocyte, skeletal myocyte?
Right. Muscle and liver and, yes, it's small intestine, large intestine.
Wow. Okay. We'll make sure we include all these papers, Bill, as well in the show notes, because this is that's actually something I've just been too lazy to personally go back and check. It's on my list of 2,000 things I want to go and check, and that's one of them. Is I always wanted to go back and look at what the association between RBC membrane level was and other tissues. The other question I had was, we've kind of glossed over it because it's a little bit of the stepchild, but what are some of the direct benefits, if any, of ALA by itself? Because you just noted that it's not that having all the ALA in the world is not really meaningful to conversion to EPA. So if there's benefit to ALA, it needs to be through ALA, right?
We don't really know. There's certainly some hints in some of the population epidemiologic studies that higher ALA intakes, presumably independent of EPA and DHA intake, is associated with reduced risk for disease. So that's a good thing. I have no problem with ALA. I just have a problem with it being a substitute for fish oils, for omega-3, long-chain omega-3s, because it doesn't. But ALA itself, I mean, I don't think it's a bad idea to take ALA products, rich oils, as well as take fish oils. But we don't really know the mechanism, but I think there's probably going to be some metabolites of ALA itself in the same sense that there are prostaglandins, leukotrienes, and other metabolites from EPA and DHA. There probably are from ALA too, that are doing things we don't know about. It's all dark on the inside, so we don't really quite know what's going on. I think there's going to be benefit, but it's not because it's converted to EPA and DHA as far as we know.
And speaking of which, now let's go down the bottom of that chain. We've talked about EPA. Let's talk about DHA. As you said, we haven't had the study that takes 4 grams of DHA, administers it in either a high, low, or normal triglyceride population. But based on studies that have looked at high doses combined and maybe trying to contrast with high dose EPA studies, plus looking at all the animal and mechanistic studies, what is your best guess as to what a high dose of DHA is doing?
In a sense, much the same thing as EPA. There are parallel mirror image molecules being made. What DHAs are called, instead of resolvins, are called protectins. These are the metabolites that are very active in anti-inflammatory processes. DHA will improve platelet function, make platelets less sticky, the same way that EPA does. Different mechanism, but the same outcome. DHA is probably better at actually lowering triglycerides and raising HDL than EPA is. So there could be actually a lipoprotein benefit there. Although DHA does raise, particularly in people who are hypertriglyceridemic, taking fairly high doses of DHA, there will be an LDL raising effect. Whether that's a bad thing or not, nobody knows, but it's been observed. And that's one of the differences between an EPA only product and a EPA plus DHA is there have been folks who've been trying to say that the EPA plus DHA products are not good for you because they have DHA, which can raise LDL. But I think that's a big stretch and misses a lot of caveats. But nevertheless, that's part of some marketing programs now, which I find unfortunate. DHA is certainly, if you look at biology at the membranes of any of our membranes, red cells or heart, DHA is by far the most common, much higher levels of DHA, like the red cell, 85% and 15%. If you look at the total of EPA plus DHA.
Yeah, I usually think of it in terms of absolute. So I know I was looking at my labs I draw my labs every once in a while. I think the last check was a few weeks ago, and my red blood cell EPA level was about 2.2%, and DHA level was about 8%. So it's comparable to what you're saying for a total of about, a little over 10%, 10 to 11%. At what point do you worry? Is it too high?
We really haven't seen any adverse effects in higher doses, and there are major international bodies that are saying up to 5 or 6 grams a day of EPA DHA is no problem.
And 5 or 6 grams of EPA would give you what level in the RBC? The highest level I've ever seen in RBC is I've had a patient who was just taking this stuff by the truckload, and which means he was probably taking about 3 grams a day, maybe 4, I'm not sure, but was sitting there at about 16% EPA plus DHA in the red blood cell. Is that
we have seen higher, but that guy is probably 99.9% percentile. We've seen people over 20 who are not taking fish oil, which is pretty. So there's some interesting biology.
What do you think's going on in there? How is that happening? They're just eating a lot of fish, or?
This particular lady I'm thinking of was, when we interviewed her, said, yeah, she eats maybe fish once a week, some salmon, but it's not like she's not doing anything Eskimo, and she wasn't taking a supplement. She was a woman of East Indian extraction, and drank a lot of, the thing that really stuck out, she drank a lot of kefir, liquid yogurt. But what in the world that would have to do with omega-3, I have no idea. So we don't know what happened to her, why she's that way. And there's other people that have been up that level. I think it's just genetic. I mean, that's a cop-out word, I know.
I know it is funny, but I was just about to say the ubiquitous cop-out of genetic, but I've absolutely seen patients who eat 1 serving of fish a week and need 4 mega EPA DHA, and it's the same brand, so it's not a brand issue. They'll take a mega dose, 4 capsules a night of the big stuff, and you might get them up to 7%. And then I've seen other people who eat fish twice a week and they walk around at 9%. You're seeing this as well, and you're equally stumped by it.
Yeah, right. We published a paper recently looking at in something like 3,500 people that have submitted blood to us and have told us how much oily fish they eat and whether they take a supplement or not. That's all we asked. And we found out that the group that has the 50-50 chance to have an 8% omega-3 index, we're reported eating 3 oily fish meals a week and taking a supplement. But below that, the chances of having 8% are diminished. But there's, even within the category of people that were not taking any supplements and eating maybe one fish meal a week, there were some people that had 8%. It's just, they're real outliers. There's a tremendous variability in the level in the blood compared to what's in the diet.
Bill, just based on your knowledge around this, and we haven't fully finished the DHA stuff, so with that caveat, do you have a recommendation for physicians or patients who are monitoring EPA and DHA levels in red blood cells for a target? I mean, the lab that I use, I think, gives a range of 8 to 10% is ideal. Do you have a view on this?
We think, in what we call the omega-3 index, which is EPA plus DHA in red cell membranes, our target is 8 to 12%. Just that's a range we think is the healthy range. Average American is around 5%, maybe 4 or 5%, twice as high as normal.
I've seen people at 2%, which are obviously people who don't supplement and don't eat fish, but I've also seen people who don't supplement, don't eat fish, and they're at 5 to 6%, which again comes back to this sort of question of the role of genetics in driving this. So let's come back to DHA for a moment. A few years ago, there was certainly a little bit of hoopla around the neuroprotective benefits of DHA. What is the state of the art and science around that particular question?
So it begins with the observation that the brain and the retina, which is really just an extension of the brain, are very rich in DHA. Virtually no EPA in the brain. Beginning with that, you have the logical conclusion is DHA is important in the brain and the eye because they're there. People have then tried to jump to the conclusion that therefore, if you give more DHA, you're going to get better brain health and better eye health. Well, that's not necessarily panned out, particularly like in depression studies. That's the most clear area at the moment where folks have tried to give high DHA products to try to affect depressive symptoms, and they don't really work. The products that seem to work to actually have an effect on depressive symptoms are ones that are richer in EPA than DHA. And so you look at a meta-analysis, a compilation of lots of different studies, the positive ones are the ones that are richer in EPA, but there's no EPA in the brain. The logic was that if the meat of the brain has got DHA in it, the actual physical flesh of the brain is DHA, then DHA should be given and it would be beneficial, but that's not a logical assumption. I think what's happening is EPA is probably providing some unique and anti-inflammatory effects in the brain circulation that's affecting, because we don't understand depression at all, but it's somehow affecting the expression of depressive symptoms like DHA doesn't. I can't say that DHA is the brain omega-3 and EPA is the heart omega-3. I don't think that's true. I don't think we can at this point say one of them is better than the other for any given system. They come together in nature. In all fish that contain EPA and DHA has both of them. It's not 50-50. It's usually 60-40 or 40-60 in terms of ratio, EPA and DHA. So I think that's the best thing to do is to get both of them at this point for any condition, all conditions.
Because you've done a PhD in nutrition, I'm going to ask you a nutrition question. If you recommend fish for people to eat, if someone says, look, I want to get as much of the EPA, DHA as I can through my food intake as opposed to supplement intake, and then being mindful of fish that contain toxins, particularly mercury, what's the best yield for safety and then high quantity of EPA, DHA? I mean, salmon seems to be at the top of that intersection, right? Is there other fish you'd put there?
Sardines, herring, mackerel, almost all the oily fish are going to have high EPA levels just simply because they have high oil, because they have fat in their flesh and their tissues. There's really only about 4 or 5 fish that are, because of the mercury, have a mercury concern, and they're fish that are really very rarely eaten: tilefish, swordfish, king mackerel, and shark. So those are the ones that everybody agrees that pregnant women, lactating women should not eat because they affect neurodevelopment of the brain. There's anecdotal stories of people eating vast amounts of tuna and getting high levels of mercury, and sure, I'm sure that can happen. But by and large, albacore tuna, for example, is twice as much EPA and DHA as chunk light tuna. It's more expensive. So it's a great source of EPA and DHA, but it has more mercury than chunk light tuna has. I think people get that balance way out of whack. They're far more concerned about minuscule amounts of mercury, and they will forego the good benefits of EPA and DHA in a food like albacore tuna, white tuna, because they're afraid of the small amount of a toxin. The benefits of eating fish, even if there's some mercury in it, far outweigh the downside of the mercury.
Yeah, I probably need to go a little further down this rabbit hole, but again, this is another example where I've seen amazing individual variability. I've seen people who eat 3 servings of tuna a week who have a mercury level below 10, on a laboratory assay like LabCorp, where the upper limit of normal is 15. And there are people that walk around at 10, so they're perfectly fine, and they're eating tuna 3 times a week. And then I've seen people who consume tuna twice a month, and they're right at the upper limits. There's a lab called Quicksilver that we use to further scratch at that a little bit and look at the inorganic and the organic. But one of the things we've learned through that is clearance matters a lot. In fact, clearance seems to matter at least as much, and maybe not surprisingly, as intake. So the Quicksilver test looks at the hair, urine, blood. It basically quantifies how they're clearing inorganic and organic, and then you get a sense, and then you're measuring organic and inorganic, so you're getting a sense of is this coming in through food? Is this coming in through, the environment? But yeah, it's another one of those things that's complicated. I mean, my general rule and advice to patients is sort of salmon and small bait fish is sort of open field running. And if you're going to go haywire on tuna, which I could do, I could eat tuna every day. I love it so much. I don't. You're probably best to at least measure your levels. But to your point, maybe we don't know exactly what the toxicity curve looks like. It's worth exploring. I do want to come back to something else on the omega-3 broad front, which is there are a handful of studies. I've seen one of them, but I believe there are others. I think one of them was the Honolulu Heart Study or something about, this has got to be over 20 years old now, that actually looked at a reduced amount of lung cancer in smokers who had high omega-3 levels. Am I getting that right?
I've not seen that. I'd like to see that, but I've seen papers recently that looking at smokers. Some of the adverse effects of smoking seem to be mitigated by a high omega-3 intake. Sort of the same idea.
It's the same idea, yeah. And maybe I'm just not remembering the study correctly, but it sort of goes down this theme of there was a protective benefit of high amounts of EPA and DHA. Let's pivot back over now to the other side of the axis. So we talked about linoleic acid, or LA, as an essential fatty acid. I believe you said we get the lion's share of it from soybean and corn oil, correct?
Right.
Linoleic acid, you described through the process of elongation, desaturation, ultimately becomes arachidonic acid. How did arachidonic acid get such a bad name? Is that all Barry Sears that we have to thank for that?
Partly Barry, partly Bill Lanz, partly Artemis Simopoulos. The way I look at it is, if we think back to the 1960s and 70s, we had this thing called the P to S ratio in oils. Do you remember that? Polyunsaturated, right? For heart health, you want to eat high P to S ratio foods, oils. The ratio mentality, that was the idea. And that made sense. We want less saturated fat, more polyunsaturated fat was good for your health, good for your heart. We move a couple decades in now we have the omega-6s and the omega-3s, and we know that they eat the L-linoleic and ALA on the omega-3 side compete with each other for enzymes to metabolize up to other EPAs and arachidonics. And so there's a competition there. So people like ratios, black and white, black hat, white hat. Arachidonic acid does give rise to several or many pro-inflammatory compounds. No question. It's a good thing. It's what it's supposed to do. The concern is, does that get out of whack and does it go on and on and on and never get resolved? But so arachidonic got this black hat idea. It's the pro-inflammatory one, and then EPA and DHA are the anti-inflammatory ones. So let's just do an omega-6, omega-3 ratio. I have a lot of problems with that ratio. I think it doesn't make any sense, partly because it presumes that the omega-6s actually are bad, and they really aren't. The evidence now coming out from large meta-analyses where people are, and we were part of this study, where they looked at plasma linoleic acid levels or blood linoleic acid levels, so omega-6 levels in the blood and arachidonic levels in the blood. And they measured it in thousands and thousands of people, and they followed them for the development of heart disease and diabetes over between 5 and 30 years. And a very clear signal that the higher the level of linoleic acid, meaning the more you eat, that's the only way you can raise it is by eating more. The higher the level of linoleic acid in the blood, the lower the risk of heart disease, the lower the risk of myocardial infarction, the lower the risk of diabetes. And arachidonic acid levels were unrelated to either of those outcomes. It was neutral. It wasn't higher or lower. It didn't make any difference.
So what's the correlation between arachidonic acid level and linoleic acid level? And what's the correlation between arachidonic acid level and ingested linoleic acid?
Virtually none. Even though we know arachidonic can be made from linoleic acid, only less than 1% of the linoleic we eat gets made into arachidonic. Very little of it's made into.
And you may have already said this, and I was too busy trying to think about something you previously said, but just as ALA conversion to EPA is virtually irrelevant, is that a similar statement for LA conversion to AA?
The same idea. When the people have given, radioactive tracers and measured how much actually goes from LA to AA, very less than 1%, very little. So, and people have also looked at, if you give a huge dose of LA in the diet, and then you measure the effect on a plasma arachidonate, no effect. If you completely strip the diet for, weeks and weeks of LA, arachidonate levels don't go down. It just doesn't respond. So arachidonate is very tightly controlled, and it's not driven by linoleic acid.
While we're on the subject of ratios, Bill, one of the other ratios that people like to talk about is the ratio of AA to EPA and AA to DHA. Do you put that in the same category of helpfulness as total omega-3 to total omega-6, or?
It's a little bit better. One of the problems with the total omega-6 to omega-3 is it doesn't define what the fatty acids are.
Right, because the omega-3 can be dominated by ALA, which is what it is. That number could be dwarfed by how much is EPA and DHA.
Correct, right. And the same on the omega-6 side. There's 7 different omega-6 fatty acids you throw into that recipe. Which one are we talking about? And so that's a problem. The fact that you can have the same ratio of EPA or of omega-6 to omega-3 with very high levels of omega-6 and omega-3 or very low levels of omega-6 and omega-3, same ratio, doesn't make any sense. And it's very hard to, the other problem is it presumes that the omega-6 is bad and the omega-3 is good. I love a quote I read somewhere then it said, the guy said, what's the point of the omega-6 omega-3 ratio? It's good versus good. So why are we doing this? AA-EPA ratio is better because it at least defines which fatty acids you're talking about. That's good. I don't think it's any more informative. It leaves out DHA completely, which I think is unfortunate. Again, it's a ratio that presumes arachidonate's bad. And I don't think we can presume that because arachidonate is not only made into pro-inflammatory, it's made into anti-inflammatory molecules too.
What drives that balance? First of all, what are the top 2 or 3 things that drive the pool of arachidonic acid? And then secondly, what are the top 2 or 3 things that drive its destination, either pro or anti-inflammatory?
That's tough to say. I don't know what controls arachidonate levels, substrate levels to begin with.
That's kind of amazing, right?
Some that you make, the tissues get incorporated with a certain amount of arachidonate, and the body likes a certain level. And it's released from membranes when you have a stressor of some kind and you make prostaglandins. But there are like 100 different metabolites you get made from these molecules. And it's almost virtually impossible to study all of them in vivo together. You can take one particular metabolite and sprinkle it on a cell in a test tube and see what it does, and then write a paper on it. But it may have nothing to do with reality, because in reality, you got 100 different molecules all banging on the door, fighting with each other, one balancing the other. It's an incredible dance that you can't replicate outside of the body. And people draw these conclusions about this fatty acid's bad and that fatty acid's good based on really naive views, I think, of the complexity of the biology. What's most compelling is let's look at blood levels of fatty acids and who's actually having diseases. Who's getting sick? I mean, I don't care about looking at metabolic charts and what pathway intersects with what pathway or competes. That's swell. But at the end of the day, if omega-6 levels are high and that's associated with reduced risk for diabetes and heart disease, that's a very powerful testimony to me that the omega-6s are good.
When you say omega-6 in that situation, is the bulk of it made up through LA, or is it a proxy metric of LA plus AA?
LA, because that's what we eat. Again, we eat, on average, we eat maybe 15 grams a day of LA, and we eat about 1/10 of a gram a day of arachidonate.
You have a bit of a contrarian view of the sort of plant oils, the canolas, the safflowers, and the sunflowers, et cetera. Many people view these as sort of unhealthy oils. Do you view any of those oils, when consumed in the quantities that Americans consume them, as unhealthy?
I thought you were going to say people, when you talk about canola and olive oil, people think those are great because they're mono. They're mono-rich oils.
Well, yeah, that's actually funny. The canola and the safflower, at least in its original form, and olive oil are virtually indistinguishable by fatty acid composition.
Well, canola and olive, yeah, but in the safflower it was like 77% linoleic acid originally. And now it's down to like 15%.
Right. And isn't it largely boosted in omega monounsaturated now, omega-9?
Mono, right. They call them high mono saf and high mono sunflower. And I think those are a problem. I'm sorry to see that happening. I know it's happening partly because the omega-6 fatty acids are unstable or are more likely to go rancid. So they like to get rid of them, which led to the whole trans fatty acid thing, but we're not going to go there today. So we're reducing omega-6 levels in our oils, which is going to reduce them in our blood, which if the evidence is pointing in the right direction, that's going to lead to an increased risk for these major diseases.
Wasn't there a day when we really didn't have much omega-6 in our diet?
Sure.
Isn't it a relatively recent thing? Like more than a few hundred years ago, wouldn't we have only been consuming saturated and monounsaturated fats primarily, in addition to EPAs and DHA?
Right. We didn't live very long either.
Well, is that really true, though? I mean, the mortality curve had more to do with infectious diseases, infant mortality, and things like that, but we certainly weren't dying of chronic diseases either. Are you suggesting that the addition of plant seed oils is protective against the things that were killing us? Or are we surviving despite them?
I don't know what the case is. I know that people have shown huge increases in linoleic acid intake over the 20th century. They do that with the intent of scaring people. Look at how unnatural this is. But then you look at death rates from heart disease rates as the levels of LA go up, they seem to go down.
Although it's so hard to look at, the problem with that type of data is that, we superimpose the use of statins and advanced cardiac life support and defibrillators and smoking. Yeah, so I think it's very difficult to do that. But if we look at the literature as far as what we can say, it seems that we're on more stable ground saying that EPA and DHA are probably protective. I'm still at a bit of a loss as to what to say about omega-6. On a personal level, I just find them kind of disgusting, if I'm going to be brutally honest. Like, I just think they're disgusting oils. Like, I think they taste like crap.
Oh.
but that's just my taste, right? Like, I think canola, safflower, sunflower, corn oil, they just taste gross to me. But I think that's because I've just acquired a taste for saturated fat and monounsaturated fat over time.
Oh, well, yeah, that could be. And most people don't eat it as oil. It's incorporated in salad dressings.
Well, but that's my point. Like, I don't know the last time I had a salad dressing out of a bottle because it just tastes disgusting relative to being able to put real olive oil on. And by the way, we should actually say, most of the time when you buy olive oil, you're not really getting olive oil, right? It's a very, very diluted olive oil. So, but assuming you're getting real olive oil, which actually has kind of a strong taste to it, away you go.
I don't like to get too far down the omega-6 pathway other than to say I don't think it's the evil that people think it is. And the problem is that we need to get more EPA and DHA in our diet, not necessarily get all hung up on omega-6.
Yeah, it seems to me that that's the bigger place to move the needle is if you can increase the EPA and DHA in your diet, the body's ability to buffer high amounts of LA seems impressive. Is that a fair statement?
I don't know about the second half. I don't know that it needs to be buffered.
Maybe buffer is the wrong word. Again, I think I use this term of like a reducing function or a capacitor, like in a circuit. It just seems like you can have people like I consume virtually none of those seed oils, like meaning I probably consume 1/10 of what the average person does because I just don't eat many processed foods and I don't have any of those oils. Like I don't have salad dressing or any of those oils in my home. So they're going to sneak in a little bit somewhere, but I'm not consuming them in high amounts.
Beets, animal products.
Sure, exactly. So you're going to get them, through those things. But if you look at my blood levels, my RBC levels, and compare them to someone who's eating literally 10 times the amount I'm eating, we might only differ by 10 or 20%. That's what I mean by there's sort of this huge buffer capacitance function to it. Whereas on the EPA DHA level, it seems that what you eat matters a heck of a lot more in the output. Is that a fair assessment?
Absolutely true. Your cells respond to EPA and DHA much more strongly than they do to changes in LA intake.
Do you think there's clinically a role for looking at the AA to EPA and AA to DHA levels? Can we infer anything from that?
I prefer the omega-3 index.
Yeah, just look at the EPA DHA total.
To me, that's the problem. The problem is the lack of EPA and DHA. If you get those up, your arachidonate levels will go down. That's the best way to lower. If you want to lower arachidonate, is to take fish oil. And so your ratios will change. You can change ratios all day long by just changing the denominator. And what I don't like about AA-EPA ratio or omega-6 to omega-3 is it distracts people from the real problem, which is the lack of EPA and DHA. It lets them run and say, okay, well, I can fix my ratio by eating less omega-6 and not eating more omega-3. That doesn't help. Whereas if you just look at the omega-3 index, EPA, DHA, that's your focus. It's too low, fix it, raise it up. Everything else will settle out.
What do you think is the best case for and against the notion that, the Reduce It study, in addition to at least one or two other studies, makes a pretty compelling case that you don't have to eat fish to get these benefits. You can get the supplements. I know that prior to a year ago, when Reduce It came out, there was still a piece of me that wondered, did you have to actually eat the fish? And is the consumption of fish itself and the EPA DHA level that rises with it more of a proxy for some subtler thing that we're not measuring?
Is the omega-3 content of fish and hence of your blood levels really just a marker of fish intake, and there's something really beneficial in fish other than omega-3 that's really doing the good work or
even complements it? Yeah. So even if you posit that the EPA and the DHA are part of the benefit from eating fish, is there something else in the fish or other things that one would eat with it that augment or transduce that benefit that you could be missed? And again, Reduce It now makes that question much less likely, or makes the answer to that question being yes, much less likely. But I want to round that out and make sure that you haven't forgotten anything you wanted to talk about there.
I agree with you. I think it can be done we prefer to do it with fish if possible, but there's a lot of challenges with that. Not only just personal taste and cost, but ecological issues. So yeah, you can do it from EPA, and I think you can do it from EPA plus DHA supplements. I think we need to talk about the other study, though, the Vital study, which was reported out at the same meeting as Reduce It. And it was widely reported. It was not done in people who have high triglycerides. It was done in normal, relatively healthy Americans, in about 25,000 of them.
What was the dose that was used?
It was one Lovesa capsule, so 850 milligrams of EPA DHA.
Yeah, and that study didn't find a difference, did it?
Well, that's depends on how deeply you want to look in the study. If you just want to read the primary endpoint.
Yeah, well, my take on that, well, who cares what my take is? Tell us your take, but starting with the dose.
You're not a standard doctor, but the typical doctor, his take on it is it didn't work, because that's what the press said. That's what the abstract said, because they were looking for an effect of less than 1 gram a day of EPA and DHA. And they were looking at a composite endpoint of 4 or 5 different elements of cardiovascular disease: stroke, non-fatal stroke, non-fatal heart disease. A composite endpoint, which 3 of the elements maybe were not affected, but one was affected tremendously. And it was heart attacks were significantly, 20% reduction in heart attacks and 20% reduction in fatal heart attacks were one of the findings. I mean, that's impressive for 850 milligrams a day. It's amazing to me that you can even do that now. And they found that if you look at people who report eating less than 1.5 fish meals a week, there was a significant benefit on the primary endpoint of cardiovascular disease by taking just 1 capsule of Lovesa. There was some really positive stuff in this study, but it was buried in the press headlines says fish oils don't work without any caveats.
If you exclude the composite metric and you just look at the CHD metric, how did the magnitude, both in absolute and relative risk, compare to Reduce It? This is one of the things I like doing to sense check studies, which is kind of do my own analysis of them and say, well, like that, again, an example would be comparing Odyssey and Fourier and saying, well, based on the fact that one came in heavily statinized, the other was not heavily statinized, durations are about the same. Where would we be fooled versus not fooled on this? Can you do that sort of analysis between these two studies as well and say, did they at least have a dose response with respect to the reduction in MI, for example?
Yeah, that's a good question. I've never looked at it that way. I've never broken it down, done the math that way. I know that there was a 9 or 10% reduction in, maybe it was 20%, I can't remember at the moment, of risk for heart disease. But again, these were not people at high risk. So your absolute risk reduction was pretty small. Relative was pretty big, but also the dose was very low.
Yeah, so you had normal triglyceride, low-risk people on 1/5 of the dose. So it's very hard to compare those two studies. Do you have a sense of what they were really trying to find out? Was the goal of that study, does a low dose of a easily accessible supplement matter in people who are healthy? I mean, I assume that's at the most basic level, that was the question.
First primary prevention study, really, that's been done. So they wanted to use it, it was planned 10 years ago. And at that time, 1 gram of Lovesa. So they didn't use a supplement. Okay. They used Lovesa, a pharmaceutical, but they just used 1 gram instead of the 4 grams indicated by the FDA. And they were looking at cardiovascular disease and cancer. I mean, it was a huge thing in primary prevention. So they found no effect on cancer, and they found in their composite endpoint, no statistically significant. It was reduced, but it wasn't significant. But if you look at certain elements of the composite, they were strongly benefited. 20%, I'm trying to think if there's a 20% reduction in MI. That's what sticks in my mind.
Do you think the most important takeaway from that is if you believe that the study had a methodologic issue that prevented it from reaching the clinical and statistical significance one would want to move forward, is the bigger knock on that study the dose, the patient population that was studied, or the composite endpoint?
All of those together can conspire to have a neutral study when there really are some good effects that are overlooked. I mean, what people don't balance is the extreme safety of these products and cheapness. We're looking at something, even 1 capsule of Lovesa. It's cheap, it's completely safe. It doesn't interact with anything. And if there's even a hint of benefit, why wouldn't you promote it?
Mm-hmm. Do you think that if a person's listening to this and they're deciding, hey, this has got me over the goal line as far as I should be using EPA and or DHA, is there an advantage to using the pharma grade product versus a reputable supplement company? Like again, I'll use the two that I like, and I have no financial ties to any of these companies, just sort of like them through reputation and having read analyses of their product, but like Carlson's or Nordic Naturals, for example.
I don't think there's a substantial difference at all in quality. There's a lot of omega-3 supplement companies that make very high quality stuff that they just aren't going to the trouble of going through an FDA approval to get it treated and developed as a drug. But it's the same chemistry.
And sometimes, I mean, if you get the EPA covered, it might actually be cheaper than the supplement. The supplements are actually not that cheap. They're actually on the spectrum of supplements that I take, when you compare, something like magnesium oxide versus fish oil. I mean, these fish oils are pretty darn expensive supplements.
It's a lot of work to get them to be that pure. One thing I'd say about Reduce It, and back to that one again, you can't buy a pure EPA dietary supplement as far as I know.
No, I think the best we can do, Carlson's does make something called EPA Gems. And I'm going to get it wrong, but the gist of it is it's sort of probably 75 to 80% EPA to DHA. So it's heavily skewed in a direction that's concentrating EPA, which is not the way it normally occurs, of course, but that's the closest you can get. And is there anything that we haven't talked about, Bill, on this topic that you would like to add? Is there any other trial that you think it's just really important that we get to?
Well, I don't think there's necessarily a trial, but if I can just get into what I do now over the last 10 years is I think measuring blood omega-3 levels are really important. And whether it's the test we do with the omega-3 index, which is red cell EPA DHA, or a plasma test or a plasma phospholipid test or a whole blood test, whatever, I just think we need to see more doctors measuring omega-3 status because it means a lot. Low omega-3 means something, and you know this. But I really want to encourage people to make the assessment of omega-3 status in their patients as important as measuring cholesterol.
Your company is called Omega Quant, correct?
Right.
And you've been at the helm of that for about a decade, right?
Yeah, this is our 10th year, right?
Yeah, 10 years. So that tells me how much time has flown because I remember when you had just sort of started that. That's a tough business to be in, right? Because just laboratory specialty labs, anything that's not sort of garden variety off the shelf tends to be sort of misunderstood by the payer environment. And this tends to be a tough place, isn't it?
Yeah, but we're not in the payer environment. We are all cash pay.
Are you? Okay, got it.
That's where the Quests and the LabCorps and the Clevelands and the Bostons are. And you used to be health diagnostic lab, of course, back in those days.
So can patients come directly to you, or do your tests have to be ordered by physicians?
People can come directly to our website and order the tests. It's $50.
So for $50, a patient can basically receive a kit from you that they take into it. I assume it's a blood test, not a saliva test or something?
It's a finger stick test.
I got it. So they don't even need to go into a lab?
No, they just do it at home and send it to us.
That's the same test that I'm getting embedded within my much broader panels, I assume, where I'm seeing the percent of EPA DHA, or is that a different company?
What lab is doing it?
Well, for example, what was True Health Diagnostics using?
Okay, True Health. So True Health took over from Health Diagnostic Lab, and Health Diagnostic Lab took my test. So they're using my test.
I see. Okay. Do you think there are other tests out there that are directionally comparable? Or, I mean, I guess you're a bit conflicted to say that there's other. Yeah, it's a loaded question. Yeah,
they're certainly directionally comparable. It's just the number. Don't do a plasma omega-3 test and expect to get 8 to 12% EPA DHA. Plasma doesn't go that high, or it's very hard to get that high. So plasma levels are lower numbers. They correlate pretty well, by and large, with red cells, but red cells are a much more stable long-term marker of omega-3 status than plasma is. So I like the red cell test for that purpose. So that's pretty much what we use in our research studies is red cell. I'd rather see a doctor measure a plasma omega-3 than not measure anything.
That's something that people can also get through LabCorp, Quest, and all of the sort of more generic labs, I assume.
Yeah, I'm not even sure they can get it at LabCorp, but Quest has a plasma phospholipid assay they do.
What does Boston Heart do? Do you know?
I think they do whole plasma.
I see. Okay. So going forward, if we're not using Ph.D, we'll have to figure out a way to come to you directly.
That'd be great. Love to do it. We got a lot of doctors who do, but and I don't know what kind of reimbursement is being paid for these tests in the insurance world. I think it's not much.
I was about to say I'm going to go with the not much box on that one.
Yeah. So,
but again, these aren't tests you have to get every 2 weeks, right? I mean, this is the type of test where you get it maybe once a year and you make a change and you look and see, hey, am I taking enough of this supplement or am I eating enough fish? And
yeah, usually about every 4 months. It takes about 4 months after you make a change in your omega-3 intake to see a new steady state.
Oh, okay. Well, actually, that's very interesting. I'm glad you brought that up. I wasn't aware it was that long, actually. I thought you could see a change quicker, but it's the life of the red blood cell, I guess, to fully turn them over.
Exactly.
Yeah. Okay, well, that makes sense. Bill, is there anything else that we didn't discuss on this particular nuanced and super enjoyable topic?
Golly, I think we ran down the omega-6 stuff. We talked about EPA and DHA alone. There is a big study that's going to come out. It should finish a year from now called Strength that is bigger than Reduce It and using the same dose as Reduce It, but it's EPA plus DHA.
What dose approximately? So that would be 4 grams total?
The drug is called Epanova. It's from AstraZeneca. It's a 13,000 patient trial, virtually the same inclusion criteria as Reduce It. It'll be about a 5-year follow-up, the same as Reduce It. And they are going to, I'm pretty sure they're going to get much higher omega-3 index levels than Reduce It did.
And again, their drug is 4 grams EPA plus some amount of DHA or 4 grams total?
It's very much like Lovesa. EPA plus DHA at around about 85%, but they're not ethyl esters. They're free fatty acids. They're unesterified.
And do you think that actually makes any difference?
Well, they're much more readily absorbed.
Oh. Because the esterified ones, presumably, is it like cholesterol where esterified variants are much harder to absorb? And you risk actually not absorbing them at all?
Well, yeah, that's the problem. It's been shown pretty clearly that if you take an ethyl ester of omega-3 on an empty stomach, the absorption is quite low, almost none, as opposed to taking it with food, which improves the absorption quite a bit. But a triglyceride-based oil or a free fatty acid, more to the point, free fatty acid doesn't require any enzymatic conversion to get absorbed at all. The triglyceride has to have, and the ethyl ester both have to have enzymatic conversion in the gut.
Well, that's actually really interesting, and I'm glad you brought that up because, as you know, a lot of people these days are fasting more and more or time restricting their feeding, and it does pose a little bit of a problem. The way I've always got around it, if I don't eat breakfast, which I don't a lot of the time, is I sort of take my fish oil at night as close to dinner as possible. But it's easier to forget that way. But you're saying another way around it is if you really just want to take these things in the morning and be done with them, you basically have to take one of the pharma grade versions because they're the ones that come as free fatty acids.
Right. It's only experimental. I mean, it's not experimental. It's approved by the FDA, but it's not being marketed. It's the only one that's a free fatty acid right now is this Epinova. The Vasipa and Loveza are ethyl esters.
So basically it'll be about a year before we even have the option to get a free fatty acid version.
That's when their study will finish. And I think it'll be as or more successful than reduce it. That's my guess.
And that will be released at the American Heart in 2020?
On their clinicaltrials.gov website, it says the studies will finish in October of next year. So whether they'll be able to
scramble an abstract, we'll see.
Yeah. Whether, I don't know.
Well, maybe when that study comes out, Bill, we'll have to sit down in early 21 and discuss it.
Love to.
Well, Bill, thanks again. This was really interesting. For me personally, I learned a lot talking with you about this kind of stuff. I just know that this episode will be one of those episodes that a lot of people end up coming back to over and over again because it is so confusing. So thank you for the historical context, the overview, and perhaps most importantly, just the sort of nitty-gritty details on the health benefits of these things.
Oh, yeah. My pleasure. Thank you very much for inviting me. I've really enjoyed it.
You can find all of this information and more at peterattiamd.com/podcast. There you'll find the show notes, readings, and links related to this episode. You can also find my blog at peterattiamd.com. Maybe the simplest thing to do is to sign up for my subjectively non-lame once-a-week email where I'll update you on what I've been up to, the most interesting papers I've read, and all things related to longevity, science, performance, sleep, etc. On social, you can find me on Twitter, Instagram, and Facebook, all with the ID Peter Attia, MD. But usually Twitter is the best way to reach me to share your questions and comments. Now for the obligatory disclaimer. This podcast is for general informational purposes only and does not constitute the practice of medicine, nursing, or other professional healthcare services, including the giving of medical advice. And note, no doctor-patient relationship is formed. The use of this information and the materials linked to the podcast is at the user's own risk. The content of this podcast is not intended to be a substitute for professional medical advice, diagnoses, or treatment. Users should not disregard or delay in obtaining medical advice for any medical condition they have and should seek the assistance of their healthcare professionals for any such conditions. Lastly, and perhaps most importantly, I take conflicts of interest very seriously. For all of my disclosures, the companies I invest in and/or advise, please visit peterattiamd.com/about.